Alright, there, we're recording. You happy? Alright.
Should I say hi YouTube or something?
You just
Like all the
did.
people do. Hi YouTube.
Alright. Okay, so I'll give it a minute. Maybe I shouldn't have started recording before we were going. Maybe we should just go though. We're gonna start with a couple YouTube videos actually. So today is all about weird shit and pretty pictures. Okay, so let's start with a couple YouTube videos. I guess I should probably link these slides, shouldn't I? Fine. Here I'll put them in the meeting but quieter thing. Boom. All right. So let's look at this. Can you see my screen? Yeah, you can. All right, cool. So this is the first one. You've probably all heard of Deep Dream at some point or another. Today we're going to try to learn how to do that. So let's start by looking at this video. So this is what a video run through Deep Dream looks like. You'll notice some slightly odd things about the picture. They've modified it slightly. Who's seen this before? Has anyone seen it before? All right, no. We're doing this. Everyone on mute. Everyone on mute. Come on. All right. Answer yes or no whether you've seen this or not. Okay.
No.
Oh, you probably think this is very odd then.
Yeah, I don't like it.
You don't like it? Well, too bad. This is what we're doing today. We're gonna do all the. We're gonna learn about all the ML that goes into making.
I love this. What the fuck?
No, when is it gonna stop? That's pretty cool, man.
Yeah.
That is awesome.
You can do it with pictures too.
I don't know what to focus on.
Oh my god.
So whoever just showed up, this is what we're doing. Just so you know. All right.
Cooper.
What?
Looks like pictures of you back in undergrad.
Oh man. All right. So that's not the only weird thing we're gonna learn how to do. Okay. So that is a slightly weirder one. But we're also gonna learn how to do.
What did I miss?
You missed this. This is what we're doing today. We're learning how to do this.
Beautiful.
There's
What is this? Convolution?
It's Deep Dream. So there's
This is what humanity will be someday.
then we're gonna do this, and there's genuinely an actual like reason that we would want to do this. Weirdly enough, and we'll sort of see why. All right. So that's that. We're also going to look at this. Okay. This is a little new thing that that Adobe added to Photoshop. And they're called neural filters, but we're going to learn how they work roughly. I'm not going to get too deep into it, but we're going to learn how we could do something like this. So here's an image of his face taken, and he has all of these little sliders that are like odd, like facial age, gaze, hair thickness, and he can slide them and actually change the image. That one's not particularly good, but look at happiness, right? He can turn on happiness, and he can slide it up, right? So this is him sad. And then if he slides it up like a little bit regular, he gets a little smile. He keeps going, keeps smiling. He goes all the way up and it adds teeth to it, right? So, like, maybe you say it's a little bit uncanny valley, whatever. I mean, he did maximize it. But how would we actually do this? This is a weird problem. I want you to think about how we would actually do this. It'll take a little while for us to get to a moment where we can actually explain how we do this today. But I want you to think about that in the back of your mind. Now you can also see he mixes multiple together. You can see it does actually do that too. This is happiness and surprise. Nice. If he adds anger to the mix,
It's happiness and not creepiness.
and it turns into this after he adds 3. So not great, but you know it's still interesting. All right, so let's keep those in the back of our mind while we learn about what we're doing. It'll take a little bit for us to actually get there. But I swear to God, we're actually going to learn how to do those things. All right? Cool. So let's talk about saliency. Does anyone know this word? I assume not. It's a word that I actually learned pretty recently, actually. Essentially, thank you, Juan. I assumed that, actually. So saliency is the important parts of something, essentially, the parts that are distinguished and are important. For us, what it means is it is the most important part of an image when it comes to classifying that image. So we want to know the saliency, like finding the saliency of the image is exactly the same as finding the part of our image that we can change so that it will classify incorrectly. So these are the parts of the image that are the most important to the classification that we are getting. So how would we actually do this? So these are the open questions. Like, how do we know what the most important part is? How do we know the saliency? How do we change our image so that it messes up? And how do we visualize what the saliency map is? I kind of gave an answer there. We're using a saliency map, but you still know what that is. All right, so let's try to answer those questions. So first up, here's a technique to actually determine the saliency. So we're going to take our image. This is a little image of an elephant, all right? And what we're going to do is we're going to occlude a part of the image, right? So we're just going to occlude a part of it and do the classification and see how it scores. So this will classify as an elephant normally. And if we take away this bit, will it still classify as an elephant? And what we're going to do is we're going to take multiple of these. So we're going to take an occlusion. Occlusion is essentially just covering up a piece of it with all zeros. So we are going to do that across the image in essentially every single place we can, in every size we can. And by doing that, we can determine which pixels correspond to importance during classification. And after we do this, we'll be able to get a map that looks something like this. So the dark areas are unimportant for classification, and the bright areas are very important, right? So it looks a little bit different than you might expect, but you'll see like the biggest highlight is right on the trunk. So apparently the trunk is actually one of the most important things to classifying an elephant, at least with our model that we've trained. So let's do a little bit of a better idea, because if we look at this, we're doing every possible permutation of an occlusion on the image, right? Anyone want to throw out a guess as to how many of those we'll need to do? That's right, a fuckload.
27.
No, that's too low. Yeah, we'll need to do a lot of these, and it is just impractical to do. So we need to do a better. We need to find a better method.
We need to have infinite.
Hmm?
Theoretically, we need to have like hundreds and thousands of these.
Yeah. Yes. Lots. A fuckload. Yeah. So obviously that is undoable. Like in big images, that's not really practical, and obviously we can find some way to do it faster, right? Otherwise, I wouldn't be talking about it. All right, so here's an idea. What if we backpropagate on the image? So normally we backpropagate onto the weights and we change the weights, but what if we did it on the image? So what if we can update the image so that it changes the loss, right? So we'll get into this a little more, and then I want to ask, what would its gradient be? All right, and the little color coding here is a hint as to that's how we're going to visualize it. All right. So let's talk about this example. You all hopefully remember this computational map, right? So what we did before was we found the gradient of this weight by doing our backpropagation here. And all I'm trying to show here is that if we want to find the partial of x1, right, instead of w1, we're finding x1. We're finding how we should change x to optimize. We can see that it goes through the very similar process. Essentially, all of this, up until this last bit, are exactly the same as they were when we were changing the weights. We go all the way back to here, we backpropagate right here, and then when we take our final partial, you might remember that this is multiplication, so we're just going to take the other variable. So when we were updating the weights, we would multiply by x, and here we're multiplying by w. So this is the only actual change between the partial derivatives, so it's very similar. We basically already know how to do this. All right, so let's see if we have some network right here. This is just a classic CNN, just 3 convolutional layers to a fully connected layer to softmax to get our scores. All right. So let's take some image, right? And this is a boat, so it says it's a boat. That's good. What we're going to do is we're going to find the gradient of this on the classification of boat. Okay. And when we do that, we'll get some image like this. So these bright spots are the importance, right? These are the things that if we changed would raise our loss. So if we moved to this direction, it would raise our loss. So this is as you remember, the gradient is ascension. So the gradient is pointing upward. So when we find the gradient of this, it is the thing that if we change, will change our loss. Obviously, we can just take the negative if we want it to be the opposite. All right. So what happens when we combine this image of a boat with this new derivative. So when we take the derivative of it with respect to loss and we add them together, what do we expect to happen? Anyone? I'm going to give you some time to digest this, think about it, and I'm going to wait until someone gives an answer. I think it's good to think about it.
Wait, can you repeat that question, please?
Yeah. So we're going to put our boat through our neural network, our little CNN that we have here, right? And it will say that it's a boat. And what we want to do is take the partial derivative of loss with respect to x, right? We're finding the gradient of loss with respect to x, right? And we get this image, right? And this image will be exactly what this is. And I'm asking if we combine these just like element-wise, like this pixel plus this pixel plus this pixel through the entire image, what do we expect to happen to the classification? What do we expect the network to do with this now, if we were to put this new image into the network?
Change the output.
Will get higher loss.
Who said change the output?
Hello.
Yeah, that's correct. Also, Adam is more correct. So yeah, because we're adding the gradient, and the gradient is pointing towards higher loss, we expect that this will make the performance worse. And in fact, we could say that, I put it there. We can actually say that it will be very bad if we move in this direction towards this. We're essentially removing, if we don't do it by the learning rate, if we don't multiply by learning rate, we're essentially taking away everything that this thing says makes it a boat away from it. So it should have a 0% accuracy of a boat. So that's not great. And here we say that it classifies as a fish, 20%. Not bad. All right. So here's a new way of doing this. Let's look at, like, if we just take some random noise, some Gaussian noise, just random pixels, doesn't matter what they are. What do we expect the class accuracy to be if there are 10 classes? What do we expect the accuracy of this noise being put into our model to be? So if we feed just random noise into our neural network that is classifying out of 10 classes, what do we expect the accuracy to be?
Is it gonna be 0?
No.
10%.
What?
Really low?
10%.
10%. That's it.
2%.
So
Wait,
it
really?
will just essentially randomly assign it.
Yeah, it's a
on
1 out of
average.
10 chance.
Yeah. It doesn't exactly work like that, but for this example, we'll say it does. All right. So what we're going to do now is we are going to do gradient descent on the image, towards the loss for boat classification to 0. So what we're doing is we are taking the gradient of our image with the assumption that the correct classification is boat, right? And we're taking the gradient of it, and we are just moving away from the gradient through stochastic gradient descent. So we're doing stochastic gradient descent on this blank image, or this noisy image, just to move down the loss. And we're assuming that it is a boat, that we want it to be a boat. Do people understand the question? Or understand what I was saying? The question being, what will the image end up looking like after we do a lot of this? What do we expect it to look like?
Outline of a boat or something.
So what it ends up being, that's pretty much right, is an ideal boat for the network. So whatever, like, what we end up with here is going to be the boat image that when we put into the network will return the highest percent accuracy, or the highest percent of score for boat. Not actually highest, like, globally, but it will give us a local maxima. All right? So this is a way that we can sort of look at our network, see how it's trained, and determine what it thinks a boat looks like, which is a sort of interesting technique. So we can, like, do this with all of our classes and see what they all look like to the network. And if we see them and they look ridiculous, then we know our network isn't really working well. All right? So we're going to talk about convolution again. I know we've talked about convolution quite a bit, but we're going to talk about it one more time. It's important. It's important especially to vision. Convolution. All right? So you all remember convolution enough, right? If you feel not confident about convolution, tell me right now, or I'm going to scream in your face. All right, cool. So we're going to talk about what we talked about last class, which is the channels. So we have our convolutional layers. Let's say that this one is it's taking color images, so it has 3 input channels and it has 10 filters, which means it has 10 output channels. Then we go to 10 to 5, then 5 to 11, and that's our output channels for the actual like 3-layer convolution. Let's say that this is our actual convolutional neural network, and let's look at this again. So when we're looking at this, and I sort of hinted at that I explained it incorrectly last time, but we have our multiple layer filters. Let's say that this one is from the first layer of convolution, second layer of convolution, third layer of convolution. Let's look at one of these particular images. So we're obviously visualizing these, right? We have a visualization of what this convolutional filter looks like. But how do we actually see this? What are the dimensions of this filter right here? If we assume that we have a neural network, a convolutional layer like this, so this is the third layer, right? What are going to be the dimensions of this image right here? It's another call and answer one, so I'm going to give you a minute to think about it. You don't need to know all the dimensions, I suppose. How many channels are there?
Oh, 11.
So there are actually going to be 5 on this one, but you are basically correct. So there will be 5 channels on each of these filters. The output ones will have 11 channels. So like you're basically right, but we're asking about these filters right here. All right. So yeah, it will not have 3 channels is the big thing. So how do we actually visualize something that doesn't have 3 channels? It's not RGB, but yet we're putting it into RGB. Anyone want to give a guess? This connects, I swear. I'm going to give you a minute to think about it again. If anyone guesses it correctly, I'll let you rename Juan again.
Genuinely don't recall.
Okay, alright. You know.
Yeah? Let's hear it, Juan.
Oh, I don't have the answer. Like,
I bet you got it. Come on, just go for it.
what was the question?
So these
How did
images
it go?
right here. These images right here are filters from our convolutional layer, right? We've determined that they have 5 channels and then some other dimensions, and we are showing them here as if they are regular images, which are 3-channel images. They're RGB, right? But we have 5 channels here instead. So how are we actually seeing this image? All right. Well, we'll leave it a secret for now. We'll get to it. All right. So let's say we have our network here, right? Essentially, what we're doing when I'm doing this is we are pulling out an intermediate feature. So let's imagine that instead of running our network the entire way through, not through the fully connected layer, we just pull it off after this convolution. Okay. So what we want to do is find the image that will maximize the output of a given filter. Okay? So we're actually going to do the same thing that we just did with the classification a minute ago when we were finding the optimal image for our classification. We're going to find the optimal image for our convolutional filter. Even though it's deep in here, we can still do that. So what it's going to look like is, here's a little bit more of the math, like a genuine math side of it rather than just hand waving. So we're going to start with a blank image, and then we're going to iterate with this following optimization. We're going to get I star, which is the optimal image, is going to be the argmax, like over all possible images, of our fi, which is going to be the firings at a given neuron, or layer if we're getting fancy. So firings at a given neuron, and then R plus Ri, which is going to be the image regularizer. So the regularizer just keeps the image from exploding into gigantic values. So we want to keep it as a regular image, essentially, and we don't want it to blow up. So we add that to our optimization. When we're maximizing a class, what do we expect fi to be? All right, so when we're doing this same process, this is the process that we're doing with all of the images before. When we're finding the optimal image for a class, we're doing the same thing. In that case, what is fi?
Repeat.
All right, yeah. All right, so this is the same process as what we did before, okay? So before we were doing this, we take some blank image, right? And then we're going to take that image and we're going to do gradient descent on it with this optimization that I'm telling you, like, in the future. And what we want to do is we want to keep grad descending until we get this ideal boat, right? So until we get, like, this new image. What we're doing later, when we're going through the convolution, we're doing essentially the same thing. We're doing this. We're taking our blank image, right? And we are doing it so that it optimizes the convolutional filters output. So these filters, we want to find the image that when it goes through this entire network, when the output of this filter is measured, it is as high as possible. That's what we're trying to do. Does that make sense?
Yep.
Okay. So we're trying to
Would it
output.
be
Yeah.
gradient ascent by chance?
So we're doing descent on the derivative when we're doing this. Gradient ascent is when we're doing the opposite, when we're trying to remove the classification. All right. So we're doing that same process, okay? So both of those processes can be described like so. We're taking the blank image, and then we are finding the optimal image. So this process right here is akin to us doing several runs of our gradient descent with some particular functions, okay? In the case of a convolutional layer, what this fi is the firings of a particular filter. So fi in this case will be when the image goes through here, it will be the strength of the output of this filter. Ri is going to be some regularizer that will keep this image, this I star, from becoming too large. Because we could overfit the image and just raise it up and up and up. Yes, Nick? He's asking a question. All right. Thank you, Nick.
I don't know why you stopped.
Well, you said you had a
This
question.
is why I didn't ask it in voice chat.
All right, all right.
Yeah. Cooper, wasn't gradient ascent associated with maximizing though? I'm a bit
So-
confused. Wouldn't you be using it for the current?
Yes, so
bias?
what we're doing, so this is not our loss function. This is the opposite of our loss function. So if
Gotcha.
we were doing minimization here, then we would be doing gradient ascent. All right? Cool. Nick, you good? Didn't sound like he was good.
I was just wondering that.
All right. So I will raise the
What's
question.
your opinion?
What's my opinion on pretzels and cream cheese?
Yeah.
I think I'm going to be on the fence on this one. I don't think I've ever had it.
Me neither. That's why I'm asking.
Oh, okay.
Nice.
Thank you, Nick.
No problem.
Good commentary. So I will go back to this question. When we're maximizing the class, so when we're not doing convolution, when we're just doing the image and we're doing the classes, what is fi? So this function is, in the case of convolution, will be the firings at a given feature. What is it when it's a classification? I think you might be being tripped up by how, like, actually easy this question is. It might sound hard, and this looks like some crazy notation. This
Will
is
it be the
notation
max
used.
firing at a given neuron by chance?
It will, but which one? So it will just be the class score of whichever class we're trying to maximize at the time. All right.
Yeah, the
So-
biggest layer.
Yeah. So it is the final layer of the neural network. It's just the output, and we are taking just the output at a certain class. All right, so that's what fi is in that case. So this is a generic function for it. We do introduce some notation, so I'm not surprised that you guys are like kind of confused here. Notation like I star here means optimal image. The arg max over I means over all possible images, we have to take the maximum of that, and then we return the image that caused the maximum, right? And then we do that. So hopefully it does make sense in the future. We also didn't talk too much about how to look at activations, but hopefully this is enough of a hand wave that you guys can believe me, and then we can get to the more interesting part of putting this all together. All right. So here are some images to visualize of maximized class images. So we're doing the classification maximization, and here are some that we can find. So we have like bell peppers, look kind of like bell peppers. Oh, you see it? You got like a gown, that looks like a gown, yeah. Pirate, got two little ships, you got two ships even. So these are what the neural network, a pre-trained one for ImageNet, would look like when we optimize to get the maximum class output images, or to get the images that give these classes the most. And you can sort of just believe me if the pieces like up to this haven't quite made sense. You can just believe me that we can do what I've described to get these sorts of things. All right? So we can do that. Neato. Yeah. I'm also going to show you, if we do this for features, we get another sort of interesting behavior. So we can look at it per layer. So if we look at layer 2, this would be the first convolutional layer, we see that the optimal images look pretty basic. You know, like we saw before, they're just sort of curvy. I mean, there is some interesting things in here, but for the most part, they are a lot more basic. In layer 3, you start to see them get a little bit more complex. Layer 4 and layer 5, similarly, it just gets more and more complex. So this is like how we get these visualizations that we like to look at, is by doing this sort of optimization over the image, which is a sort of new idea for you guys. All right. So now we're going to talk about a different task very quickly, because we're going to have all of these things come together to give us Deep Dream. All right. So we need to talk about localization. Localization is the problem of not only classifying an image, but determining where in the image the thing we're classifying is. All right, so if we're doing this, we want a good box around the elephant, and we also want that if we have a bad box, that it does not return the same thing. So really, we're going to first classify the image and then determine where it is. I'm going to skip over a lot of the techniques that we use for this, and I'll just give you a simple one. We can talk more about them if people are interested, but it might become a little bit heavy if we get into it too much. It's some large-scale networks. If you want to look up RCNN is what we use in general, is RCNN, and then there's faster RCNN, or no, there's RCNN, then there's fast RCNN, which is much faster version of it, and then there's faster RCNN, all made by the same people. They just kept improving their model, and they got it to work very quickly. So it's worth checking out. But for now, we're going to talk about a different technique. And I'm going to ask you guys how we might do this. Anyone got any ideas? So what are the outputs of this task? All right, what does our neural network need to output?
Is it the percentage of a classification
Mm-hmm.
or a feature?
So it needs to output the classification of the image, right? But we also need to get this box out of our network. So what do we need to get this box?
Locations of the
Yes.
pixels.
The locations. Well, that's basically right. Let's take a look. All right. So here's the basic idea. I'm again not going to get into it too much, but I will give you a little teaser of it. All right. So we're gonna have our network, right? And this is just before we had an input, then 3 convolutional layers, and now we're gonna have a classifier So this is just going to be a fully connected layer that we will treat as our classifier. It could be multiple also, but we're just going to treat it as one. And this is going to output our class scores. We're also going to have a regression network, or regression layer at least, attached. And they're both going to take the same output. And our regression layer is going to output the box bounds. So this right here, this box right here, is called a bounding box. And what we are returning are the bounds of that bounding box. So that's a little bit of a mouthful, but what we're going to get, so what do we need? What is the minimum amount that we need to uniquely identify a box on an image? Use your creativity. Yeah.
2 edge points.
That's just about right. So what we're going to take are two sets of points, the x1, y1, and x2, y2, and we're generally going to use the upper left and bottom right corner so that we can determine the exact box. We can just draw the box like that. All right? So that is, in general, how we're going to do it. So then, how do we determine what the loss is for the bounding box? How do we determine how good our box is? We could do simple regression. So if we just take like any given image and we give it a box that we expect, we're going to be given that on our images. So we have our image here, and we're actually going to be given this box, and we're going to be given the classification, and we're going to make some new box. And when we make some new box, how do we determine how good it is? What I'm suggesting when I say that we do simple regression is essentially we just take the difference between this point and the difference between this point and this point, and then we say that that's our loss, right? We do either like we square them or we just take the absolute value of them, like we've been doing in very simple neural networks. But that doesn't actually work quite well. So could we minimize anything else? There's a lot of ideas here that you could come up with. Does anyone want to give an idea? So if we have two different boxes. Yeah.
Can we calculate loss by taking center point of two boxes and finding the distance between them?
Yeah, we definitely could do that. That is slightly different than doing the regular regression, and it might just work. It's not the answer that we're going to use for this, but it is a correct answer. So what we're going to use is the Jacquard index, which is a fancy-sounding thing for something very simple. So the Jacquard index is going to be between two images, or two boxes in this case, is going to be the intersection of those two things over the union of those two things. Essentially, it is how much of them overlap. So we're just calculating off of how well they overlap. And now the question is, that I'm going to ask you guys now, is will we maximize the Jacquard index or minimize it? Do we want to maximize it or minimize it?
Maximize.
You want to get it to 1.
We are maximizing it, yes. Yeah, we want it to be 1. As ours gets worse and worse and worse, this will become 0. So we're going to want to maximize that, and of course that doesn't work super well as a loss function. So what we're actually going to do is we're going to use a different function that is identical, basically, that we call the Jacquard distance, which is 1 minus the Jacquard index. So this is what we're actually going to use as our loss function for our regressor. And basically all we're going to do, I think I don't expand on this very much, but basically all we're going to do is we are going to both find the loss for the regressor and backpropagate it, and we're going to find the loss for the classifier and backpropagate it. Something that does happen on occasion is we're going to freeze all of these layers. Freezing it just means that we're not going to update them at all, so we'll only be updating the classifier and the regressor, and we're going to keep all these features just because we have good features to work with, presumably. You could also just train this from scratch if you'd like, but there are problems with doing that. So in general, we're going to freeze it, and then we're going to train this one on the Jacquard loss, and we're going to train this one on our regular loss that we used before. All right, so that's Jacquard loss. All right, so what will happen if we search the image for all of the possible classifications, right? We check every one of these little boxes, and we see which ones have a, like which class is the highest there, and then we want to maximize those using our method from before. Anyone want to give a guess as to what will happen? I'll give you a hint. It's really weird. This sort of thing happens. So this is Deep Dream, like we were looking at before. What we're going to do is we're going to do some weird shit. Looking at any of these boxes, we can see that this right here was originally classified by our network as a dog, as most like a dog at the very least. And then what our network did is optimize this little crop of our image to be as much like a dog as it possibly can be, with this crop being the starting image. So that's what we're going to be doing, and this is actually how we get Deep Dream to work. So we're going to need to have a localization network, and then we're going to need to optimize each of these, all right? Each of these images. All right. So I want you all to like take a minute, right? Even if you got lost somewhere along the way, I want you to think about this problem, about taking an image, looking across it, and maximizing. You don't like it?
That looks gross.
I think it
Sorry,
looks
it's got
tasty.
back. That looks disgusting.
Well, we want to figure out how to do this. All right,
What kind of fucking dog is that?
pasta dog. It's an Italian.
It passed away.
So we have the problem of taking an image and finding any place on the image that remotely looks like something and maximizing it so that it looks a lot like that something, at least, you know, relatively. And I want you all to take some time, to genuinely take some time, and each like write out your own possible solution for how we might want to do this. Bonus points if you use everything you've seen today. We're going to have to do that to do this well, but you can try to come up with your own method of doing it. I'm going to give each of you a couple minutes to do this, and I would like you to genuinely try to come up with a way to do this. Sound good to everyone? It doesn't have to be precise, I just want to hear some ideas. In the meantime, I'll describe the problem while you guys think about it, just so that we get a on the same page, all right? So we're taking some image, right? And we're going to use our, so I'm not going to describe that word, I guess, but we'll want to find any place on here where we say like, so we'll say like the probability of dog, we're going to treat it like probability, is like 0.6, right? So we say that this is kind of like a dog. What we want to do is change it in some way so that instead of 0.6, we get something a little bit higher. And we want to do that across the entire image. So we want to do it everywhere. So the question is, how on earth do we do that? So do people understand the problem? I just want to make sure.
I think so.
Okay. How about this? If one of you guys can genuinely give me a compelling and like good good argument for how to do this, I'll give you like a special officer role.
I have
Genuinely.
an idea. I was waiting a bit longer.
Yeah. All right. Yeah.
Okay.
I'm gonna
So
wait
can
some
we
more
sum-
time too.
Oh,
Yeah.
should I wait longer?
A little bit. Yeah.
Okay.
Yeah. I think like people will probably come up with ideas very quickly, like at least some ideas, just because they can connect what we've been talking about. And this goes for you. I'd say like try to think about the actual problems that go into this. Like we are going to have variable sized boxes. We're going to have a lot of different classes. We're going to have overlapping boxes. How do we deal with all of those things? Let's say 1 more minute. All right. All right. That's time. That's time. Could everyone unmute now, real quick? All right. Hi, Chris. So, who was able to come up with something? It doesn't matter, like if you think you're confident about it or whatever. It doesn't really matter. Just who was able to come up with something?
What I was thinking is you could use like the ideal image we computed earlier,
Mhm.
and you kind of overlay that onto the box. You can maybe warp that image around just to make it still fit in the box. And I was thinking if we somehow emphasized it so that like the parts of the ideal image that overlap the parts of the box that are strongest, most like a dog, you can kind of like use that, focus on the parts that are most like a dog to emphasize it. I guess emphasize out the ideal image. I was thinking that kind of, if you look at this, there's a lot of eye splotches
Yeah.
on the pasta where there's dog eyes, but nothing around there is really dog besides just the eyes. So
Yeah.
Yeah.
Yeah. This is it's pretty awful, isn't it?
I wouldn't eat that pasta.
Yeah. So there are a couple problems with what you're saying, but I do like the idea. So some of what you were getting at was like, so you said like stretching and fitting the optimal one that we got earlier onto them. That wouldn't exactly work because like, as you can see here, like a lot of them look very different. I don't have any great examples, but a lot of them, like these eyes
Yeah,
will
like
look
the
very
dogs are fixed in
different.
different ways and stuff.
So we don't actually do that. It is an interesting idea, and what you like could try doing instead of just mapping that ideal image is sort of morphing them using your ideal features. That would be an interesting approach, and there is something to your idea. I just I think I can't give you the officer role. I'm sorry.
Darn, tragic.
All right. Anyone else want to share an idea they came up with? I don't mean to blast them. I'm genuinely curious, and it's an interesting like thing to just try to figure this out because it's a very hard problem. I don't think like don't feel bad if you don't get it. Anyone?
I don't know. I can just give it a try. Like
Yeah.
in our last convolution layer, whatever features we get,
I'm gonna
we
draw
can
it for you.
just add all the features in one image to get a final image.
So okay, here let's so we have our 3 convolutional layers, right? We're gonna feed in the image. All right, let's work through it. So we're gonna feed in the image into it. So you're saying we take the output of here, right?
Yeah, we essentially take output of each filter
Mm-hmm.
and mix all that output, first converting them into 3 channels because we want our image to be 3 channels.
So
Like we
what?
did in example earlier, like how do we extract features out of.
So one immediate thing that we didn't get a chance to talk about is let's talk about turning a like so 2 by 2 by 5. Let's say it has 5 channels into some like we want to reshape it. We could talk about doing it so that it's like oh man, I picked bad numbers. Okay, well we can reshape it, right? So if we reshape this into being 3 dimensions, do we necessarily preserve it?
No.
We don't. You can think
No.
of it, so you can see this pretty straightforward. If we think about taking a sphere taking like multiple points on a sphere, right, and trying to project them onto 2 dimensions, right? So if we try to present it, try to put it into 2 dimensions, so let's use r squared, into 2 dimensions, we see that we'll end up with a, I won't use that, I'll use this. We see that we end up with, like, for one, like, overlapping points, like, multiple will go to the same place. We also, like, can't retrieve the actual image from it. We'll lose something in doing this projection. And in going from, like, high dimensional filters, usually we'll have, like, you know, high channels. Like, imagine we have 11. Going down to 3 dimensions basically, going down to 3 dimensions basically, like, ruins the use of it. So that part would make this fail. You're also talking, so you're saying we're going to take each of these and then combine them? I don't really know what you
Yeah.
mean by combine them.
Like we can do multiply or add or something.
Just like multiply them all together?
Not
Get some
multiply as
simple
in multiply. We have something in Photoshop called multiply, which does something to merge to image. I don't know what exactly it does at
Dot
back
product?
end.
Okay. It's probably a dot product. It's probably a matrix multiplication. I'm not sure, but I can't really see a way that this would work. Not to say that that you're wrong necessarily. Mostly that I just don't. I can't quite see how this would modify the image in a way that would cause like more dogs. Yeah, that's okay though. That's okay though. I really do genuinely appreciate the effort and I like it. So I'm gonna give Adam and wait, who else answered? Nick? No.
Me,
Max.
Maxwell.
Max. Yeah. Sorry.
Everybody is Nick.
We're all Nick.
There. So you guys both are in this very special role now. I'm
Oh.
kicking out everyone else. It's just you guys. All right. Cool. All right. So let's hear about how we might actually do it in practice. All right. So what we're going to do is we're going to start with a network, okay? And we're going to use a pre-trained network. Could anyone answer very quickly why we might want to use a pre-trained network before we start doing?
Training takes time.
Saving time?
Yes.
I mean, kind of, yeah. Really, like what we're doing is these. Like, if we have this network, if we train this network on a bunch of things, we'll be able to use the features that we develop in actual classification and boxing and localization. And by doing that, we get very good features out of here already. So when we use those features to do the classification and the boxing on new images, we expect they'll be very good from the beginning, and we can leverage already trained features that we trained in an environment that's a lot easier to train than it is to train in what we're about to do. We can't exactly train them while we're doing our thing. We can train these pretty well, but the features won't really develop correctly. All right. So we're going to start with an image, right? And we're going to do our localization and classification on the image, and we're going to look for the place that is most likely something. So we're going to take the image, it will classify it as something, and we're going to essentially highlight that, and it will say this is a dog with 10%. Then we're going to do our practice that we did before, where we take this crop, right? We're going to take this crop, and we're going to do optimization on it. We're going to do our gradient descent on this to maximize the percent of dog, all right? So we're going to do that, and then this little patch right here will be changed in some way to look more like a dog, and now it will be 99% a dog. Essentially, what we're going to do is we're going to do this across the image, and the thing that is probably going to trip you up, and the thing that probably was keeping you from being able to come up with a nice, pretty solution, is that we need to get all of these possible boxes. So we found one here, and we can do that just by classifying the image and finding the box, passing it through here. But really what we want to do is find all of them that are within some boundary for us. We want to find all of the possible images on here that would be highly classified. So we want to do that across the image, and we want them to be disjoint from each other. We have a network, RCNN, like I was mentioning earlier, that is able to do that. So we're going to have to use some technique to do that, and then we also need some way to convert these images all into some uniform size. Again, RCNN will take these images of varied size and will squash them into the correct size and then feed them into the network. All right, so we're going to do that, and then we're going to do our classification optimization. And then we'll do that across the entire image, and then you'll get something like that, which is pretty great.
Does it bark though?
I think it more screams in pain. Yeah.
Wait,
Yes.
so what do you mean by disjoint?
Non-overlapping.
Okay. So it couldn't be like that new 99% dog might have a dog within it.
So when we are doing it at it can. When we're doing this at the beginning, we can do it like for all of the I forget what we call them, but they are places of like crops that are important that have high classification. So we can find those and we can do it on the image, and then we can do it again, ignoring the very like big patches, and then we can get multiple inside of each other.
It would depend on if it was dynamic in size though, because if it was dynamic in size and some could be smaller patches that more fit the description, then it could just be that if there are two near each other, it would have those individual different ones.
Yeah, so we can handle the dynamic size and all of that, so it's okay. It's a very nice network. You should really look up RCNN. It's how we have this. You can thank the people who designed RCNN for this. You can also thank Google for this. Google developed Deep Dream. It's really great, isn't it? All right, so cool. Now we're going to talk about the other one, the Photoshop video. So with all of this in mind that we've just learned, what's the same between them? I guess I'll just keep doing the waiting thing. Just if you have an idea, and I'll say this for your sake, don't be afraid to like just guess and be wrong. It's fine. Like you could say nonsense at me, and it's honestly appreciated, and it'll probably help you learn a little bit more. So like. You don't need to all mute there and be so worried. Just like shout something out.
What is the Photoshop one?
So the Photoshop one is that one. So you remember that we had the it was a guy with the sliders. Were you here at the very beginning?
I was getting my pretzels, so unfortunately not.
Oh man. Okay. Yeah, I think I posted a little bit ago actually in reading material. Here, I'll repost it here. Yeah, I posted it here. I posted the Reddit post actually, but I saw this on Reddit and I thought that it would be interesting to show you guys how it worked. Okay. So what we have essentially is it will take an image of a face and it'll give you options, different sliders of what you can change about it. The difference here is that he's moved the slider up on the happiness bar. So there's a whole bunch of different options, and you can slide them all to change them how you'd like. And you can see that his face has changed. He has more of a smile. His eyes, his eyes are basically the same. But it has changed the image slightly, right? And what we want to do is we want to be able to take an image of a face and do this to it. So does anyone have any ideas just off the bat?
Like what we did for Deep Dream, we can essentially do the same here. Somehow.
Basically. I mean, there is a lot that's the same between them. So I asked particularly here, like, what is the same, and implicitly, what is different about the two methods?
Maybe something different is that this one will only do it in like one box, like it'll only do it once.
Absolutely, that makes the problem a lot easier. Yeah. Yes, absolutely. So that is a good limitation for us. It makes it a lot easier. There are a couple other things that are different if anyone wants to try to point them out.
The person does not turn into a chihuahua.
That's true. Technically correct. Thank you, Chris.
Because I was curious, because the spaghetti one,
Mm-hmm.
it used
Yeah, the spaghetti one here.
Did it use like reference images of dogs?
So that's the pre-trained like classifier. We're going to have a pre-trained classifier that will already be trained to identify images of dogs. In particular, I think in general, these ones, a lot of the Deep Dream ones you see are off of data sets of either dogs and cats or of ImageNet. Generally, they're trained on ImageNet, so it's a bunch of different classes, but for whatever reason, dogs are a reoccurring theme. Lots of images of dogs in Deep Dream things, which is interesting. You can try to argue why. That'd be interesting. But it is a pre-trained classifier, so it already knows how to identify what a dog is. Otherwise, this whole process wouldn't make any sense. We just get random noise out of it. Yeah. That make sense?
Mm-hmm.
Cool.
So the Photoshop one is pre-trained to classify people smiling.
Yeah. Yes. Absolutely. So that is a good point.
Categories for what it implements later.
Yeah. So we'll get there. Okay. Cool. Nice.
I've also noticed it only generates on a specific area, like the mouth, and not like every single area that has anything flipping a mouth.
Yeah, no, that's a good point. We can talk about that later too. So here's a rough walkthrough of how it works, okay? So we're going to take an image, we're going to crop the image to take out the face, or in the case of the smile, we may take out the mouth. It depends on how we want to do it. We're going to feed this through a network, a pre-trained network, and I was going to ask what should the output be of this net if we're trying to maximize him smiling? And we're beat there a little bit. It is the happiness score or smile score, whatever they used. So we want to have some ability to classify if it is happy or if it's angry or if it's surprised. Those are the three options on the video. There are actually a lot of networks that can do this very well. So we can just take one of those as pre-trained networks, feed in the image, do the thing. And then we're going to, so then we need to talk about the slider, okay? So we have a slider. How do we modify our idea from Deep Dream so that we can use a slider? Anyone want to give me an idea? So we can go full happiness on it, or just like half happiness, or neutral, or negative even.
We have the happy score, that means output of the convolution, output of the network, and we can just back propagate it.
So we are going to, instead of just strictly maximizing what we're doing, we're going to maximize or minimize the difference between the score that we produce from the image and the score that we want, which we determine from the slider. So we're going to just minimize that difference instead of just maximizing the score outright, because we don't want it to be maximum happiness in any given situation. So we can do exactly that. So all we have to do then is take the crop, optimize it so that it gives us the chosen score. We can use our optimization just any sort of difference we want, and then we can use that. So we can just determine a simple loss between the output of this with our crop and the output that we want, and then we back propagate onto the cropped image, and we'll get a new crop after doing several iterations of that. And there we go. We can change his face. All right. So that's the Photoshop thing, very roughly. Now let's talk about something that is a bit of a surprise for you guys, but is also a bit of a teaser. Style transfer. Style transfer is one of the absolute coolest things in machine learning, at least in vision. And I guarantee that you guys have used it before. In fact, most obviously, probably a lot of you have used Snapchat filters that change your face to look in a different style or look like something else, whatever you want. This is how they're developing the new age ones that are really good. So here's an example of what style transfer can look like. So we're gonna put one image in the style of another, and it will look something like so. So here is the reference style of so this is like Monet, Van Gogh, Cezanne, I don't know who that is, and ukiyo-e, I don't know either. So you see that we can take an image, and when we feed it through our style transfer network, we'll get an output of the image in the style of our reference image. So these don't actually show them, but there are a reference image for each of these. We can also take reference styles, or reference features, but we'll talk about that more later. So what we're like, huh? It looks pretty like fucking cool, right? And they look really good.
Realistic.
And you can Google some of these. They look really good. And you can see how good these paintings actually like come out. And there are a lot of different things that we can use to like get this sort of style. All right. So I want to ask you guys again to take a couple minutes and try to guess if you can figure out, or try to figure out if you can see how we could use the things that we've talked about today to do this. I'll give you like 5 minutes on this one. This one is a hard problem, by the way. It's very interesting, and I'd like to hear if you guys come up with any creative solutions for it. But I'll give you some time. Give some time. I think there's probably some more examples out there. Here, I'll pull up some more while you guys think. Try style transfer. Let's see.
Don't you have an example of last year when
Look
we
at that.
spaghettified people?
When you what?
You know, spaghettified people?
I don't remember the example.
It was the style of spaghetti where basically everything was turned into macaroni, and we applied that macaroni style to all of our photos. We have a spaghetti item.
I don't remember actually. That sounds like fun though. Yeah, I'm showing you some more examples. This one, yeah. So these are still different styles. There's some other things that you can do with it that are interesting. Like you can move it more towards one style than the other, and it is interesting. Yeah. These are one of the coolest things to code up yourself and just like run on your images. It's a lot of fun. Yeah.
Is the Photoshop thing like already out on like the
I think so.
Photoshop?
I think so. I don't know.
Have you ever messed with it?
I haven't. I don't use software that costs money. You kidding me?
Pirate Bay stuff.
I was gonna say,
no.
dude, just Pirate Bay it.
Yeah.
Are we allowed to endorse that in a UMass club?
Who's gonna stop us? What?
I mean, it's being recorded, right?
Yeah.
Oh shit.
Yeah, I'm posting it to YouTube. Everyone's gonna see this. The last video, the last video got what, 40 views? So you're donezo.
Oh no. I'm gonna be a TED Talk soon.
Let's
Thanks.
see, 42 views. Oh no, actually that's my other one. That's
Oh,
the
perfect.
yeah, 46 views even. Oh my god. Oh my god.
That's perfect.
You guys are donezo. All right.
You don't have face cam right now, though.
No, I do. It's just only on the recording, not for you guys. I can't do both. Yeah. So on the actual video, you'll see me here. Like I'll stick my tongue at you. Bleh. Yeah. You can't see it though.
Bet.
Not until it comes out on video.
So wait, if you take a picture of you smiling and then you crank up the happiness more, does it make you like smile more?
I have no idea. You can try it.
It makes you smile to your ears.
You could be approaching its it might have a maximum, like because it's just a classification. So if it classifies you as already like close to 100% happy, it probably won't change it very much. The gradient will be small.
Yeah, fun, not a fact. Keanu Reeves has an 100 on the happiness score.
All right.
Yes, there wouldn't be a problem because mostly college students use Photoshop.
Cooper.
Yes.
So when you used the happiness slider on the Photoshop image, there were like artifacts to the right side of the image. Like the more he scaled up the happiness.
Mm-hmm. Let's see some of
Is that? Yeah.
It's a little bit that's just it assumed that there should be a shadow there, and for whatever reason, there being a shadow there makes the original neural network think that they're happier. I'm going to throw out a hypothesis that people who have their picture taken in a setting where they need flash are more likely to be smiling more, which is why there's a little like background shadow. That's my hypothesis. Very unprovable, but yeah. So that it thinks that there should be a shadow there. Because then the convolutional layer would think that there's a starker difference here, which maybe it does.
My
Anyway.
hypothesis is that the convolutional layer caught that there was actually an invisible person behind him.
That
Can't prove it.
That was so laggy, it took like 30 seconds to come through. It just sounded like you were talking in slow motion.
I think I understood 3 words out of that.
I think he said that the convolutional layer thinks that he's happy
Oh,
because
that's
there's a
so
ghost
sad.
behind him. Yeah. I got it, I just had to listen carefully.
No, can you hear me right now?
Not particularly. You are breaking up
Yeah,
like
no,
everything.
I said I think it caught an invisible person behind him.
Ah.
Oh my god.
Do all happy people have ghosts behind them? Is that what you're saying?
Yeah.
Maybe. All the training
Maybe
people, at least.
they're haunted.
Testing.
Alright.
Yes.
Alright.
Yes.
Alright.
Yes. That is exactly what I'm saying. I've proven ghosts. Get at me. Fucking network.
Alright, that's 5 minutes now. Alright,
So
alright.
also, okay.
Okay.
So the Photoshop one had a slider for hair, right?
Yeah.
So what if like a bald person went there? Would it automatically assume what their hair color was?
It might.
That's a good question.
You should try it.
Maybe it would make it the hair color of their skin.
Maybe it would make it the hair color of the ghost behind them.
Alright. Who wants to talk about how they think we might be able to do this? Anyone?
I think it's black magic.
Black magic? That's a pretty
Yeah,
good
but-
guess. That's a pretty good guess. It feels like it, doesn't it?
It's a black box, so close.
Black magic box. Got it. Alright, I guess that will be the official response from the club. I like it. Anyone else have anything they want to shout out? Just any thoughts? Like how this could possibly be possible. Alright, fair. Alright. So I'm not going to talk about it today. I'll talk about it more properly next week. I can give you a description if people really want. I could do it with a on Sketchpad, but I do want to save it until I have a better lecture on it because it requires a bit more talking. There's a couple things that go into doing this. The gist of it is that we're going to take intermediate features between the image and the style, and we're going to change the image so that its intermediate features match. And then we're also going to keep a record of how closely related the images are in terms of like actual like values, and we're going to want to keep that fairly similar too. And we end up with some pretty cool results. I won't say more about it, but what we're going to do now is doing some code. All right. You thought there was no code this time? You were wrong. You probably did think there was code this time. I've had one every time. So if you don't have a GitHub, make a GitHub. If you don't have Git, download Git. And here is the official Google Deep Dream GitHub page. So I'll load that up so you can see it. So on here they have a couple images, but they have a notebook. So if you go on here, it is they use Caffe, which is a different neural network simulator. I think this was actually developed at UMass. Fun fact. And you can run through here and you can figure it out, and it will actually do Deep Dream on whatever images you put in. So you can put in images of yourself. You can see what wacky shit you get, and you can like do that. I'd suggest you all play around with this. You clone it. You play with it. See if you can get it to do anything interesting. You'll notice here, by the way, this image right here looks a little bit more normal, if not like a bit weird, than say like this one. what's happening is that this one right here, instead of maximizing the image class, is maximizing the image feature. So it's picking a layer of convolution or a particular convolutional filter and is maximizing it. So we imagine that there is some filter that is like a stark line, and it is maximizing those, and it looks very interesting, right? But then when we want to maximize classes, we get this wacky shit. So it's sort of a demonstration of the difference between them. Yeah. And this one is an intermediate one. Yeah. Cool. I also included on here the style transfer, or a style transfer GitHub page. This one is essentially, it allows you to do some style transfer between images. So it's like this one plus this one equals this one. Again, I recommend you try downloading it and just running it on your own, and you can see how it trains and how well it does. So you can see that it takes multiple iterations for it to actually become like the image you want. So after one iteration, it looks like nothing, because we're actually going to start with a blank image when we're doing this. So we start with noise, and it looks a bit like them, so this is one iteration of training, and then over time, you see that it actually starts looking like it. Nice. So I'm going to ask that, I can't enforce this or anything, but download both of these Git repos. So just clone them on your computer and try to get both of them to run. This one is, again, also a notebook. It's pretty common practice to use these files, which are notebook files. You've all seen them. So you have to download these, and then you can run them. Yeah. So I guess that's our time for today. If anyone wants to stay and just work on this here, try to download these, get them working, that's cool by me. If anyone wants a better explanation of how we actually do style transfer, I'm happy to stay and talk about it. But I'm going to stop the recording so that, you know, I guess today is just about what we covered, I guess. So I can save this for a better lecture. All right, cool.